So the indirect Fick equation is what we have here. Indirect Fick uses VCO2 or CO2 contents and not oxygen. Oxygen is the direct Fick version of the equation. And this relates delivery or addition or extraction of a substance from a medium to the flow of that medium and the concentration at two endpoints. And so in the circulatory system, we have the beginning and the end of a tube, or across the lung, as our difference in concentrations. And then the rate that we add a certain item is related to those concentrations and the flow of whatever the medium is. So air in this case, blood in the case of O2. But this is the equation that we can put numbers into directly if we have all of these other values to calculate cardiac output. VCO2 is easy. We looked at that on Thursday. It's often given to you. And we were almost done the arterial CO2 contents. We had calculated arterial CO2 pressure, and we were converting that to contents on Thursday when class ended. You won't get contents from the metabolic cart itself. You might get pressure, or you might get percent. I'd like you to start with percent and work your way through the calculations like we did, but percent doesn't matter. We need pressure represented by that percent, and then we've identified that while arterial CO2 should mimic alveolar CO2, those should be in equilibrium. Alveolar CO2 doesn't necessarily get reflected in the sample that you take at the mouth, end-tidal CO2. It gets diluted as it comes out of the lungs. So we just finished correcting for that dilution between end-tidal measurement and then the alveolar CO2 of interest. And the number that we got was this value here, 41.44 millimeters of mercury. That's the corrected value. We would have measured slightly less than that. That typifies the dilution that I just talked about. And now I want to turn that into contents, because partial pressure doesn't allow me, it's not a concentration. It's not a concentration, but we can describe concentration with that partial pressure number. And the equation is a standard equation that I presented in class on Thursday. This is just the relationship between pressure and contents. This is specific to CO2 and it's specific to blood. So if there is a pressure that you can measure in blood, the contents will be related to pressure according to this equation. It's different for oxygen because it has a different tendency to dissolve in a fluid. The contents can change. So this is a standard equation that you would simply plug a number into to get contents in mils of CO2 per 100 mils of blood. It's a concentration. So I'll do just that. The newly found partial pressure of CO2 in the arterial blood, in the alveoli, what we just corrected for, I put in the place of PaCO2 here. And then it's just resolving the equation using your fancy calculator. 41.44 to the power of that decimal point is 4.46 times 11.002 gives us 49-ish mils of CO2 per 100 mils of blood. But I'm not stopping here. And I should have done this before I posted the slides for you. I went and edited them so that the units would be consistent. You have a set that follows suit. We don't want per 100 mils of blood. At some point when we do that calculation, we need to have per liter of blood, liters per minute. Blood is in liters, so I'm correcting this right now. Instead of leaving it as mils per 100 mils of blood, I want to know how much is in 1 liter of blood. Simply multiply it by 10. There are 10 100 mil bins of blood in a liter. So 490 mils of CO2 per liter of blood. That's the number I'm going to carry forward and use in the equation to calculate cardiac output. And it will become clear when we do that final calculation why I made this switch now to liters of blood, mils per liter of blood. If you want to, at the risk of adding a layer of complexity, what I'm revising in the slides for next year is I'm going to change the equation to, it'll just be 110.02 times the PaCO2 to the same power, just to get rid of the conversion step at the end. It's the same equation if the trace were drawn on the mils of CO2 per liter graph. But I digress anyways. This is the final number that we can put in this equation, and if we have all three terms, we've accounted for 2 so far, we can calculate cardiac output. So we have VCO2, that's done. We have the arterial CO2, which we measure at the end tidal breath at the mouth. This is in mils per liter of blood. We just did that conversion. And so we need a comparable number for venous CO2, also in mils per liter of blood, to allow us to resolve that term. Venous CO2 in mils per liter of blood. Much like with arterial CO2, we're not going to start with contents. We have to convert from percent or from partial pressure to contents. But this is what we get from the rebreathe maneuver. And some of you have done this now and have the experience of it, but the theory is the same. You are clamping the lung bag system, bringing CO2 into equilibrium. It's accumulating in the lungs. And as it accumulates, the point where it would reach equilibrium is the point where end tidal CO2 would match venous CO2. So we want to find that point where equilibrium occurs. The problem is there's no one end tidal value that represents the equilibrium. There's not one number that you can pick out that tells you, oh, I can plug this into an equation. This is the point where venous and end tidal CO2 is in equilibrium. That's not the case. Not one number will allow you to measure venous CO2 contents. And so in a normal situation, we'll simplify the respiratory and circulatory systems as follows. We have the partial pressures of CO2 listed here. So on the venous side, it's higher than arterial because all the tissues that are active add CO2 to circulation. And that, of course, gets offloaded at the lungs and dissipates normally. But you just went through the activity of clamping the lung bag system using that the rubber rebreathe bag. So there's nowhere for this higher PCO2 to dissipate. It goes into the bag, and then you breathe it back in, and then back into the bag, and you breathe it back in. It accumulates. It doesn't only accumulate in the bag, it accumulates in the entire lung bag system. And this is complicated by the fact that your heart doesn't stop beating, right? Unfortunately. So while you are coming towards an equilibrium in this closed system, that abundance of CO2 is now also being transported out of the arterial side of the heart, and the arterial PCO2 is increasing. So where it's normally 40, it's starting to creep up. And then as the blood continues to circulate, we have more accumulation on the arterial side, and eventually there's going to be a point. There's going to be a point where this extra CO2 circulates back to the venous side and then contributes to this lung bag system. We want to make the measure before that happens. we want this closed system to accumulate CO2 and reach equilibrium, and we don't want it to be artificially high because some CO2 is circulated through the arterial system back to the lungs and is artificially increasing CO2 further. So we can clamp the lungs closed. We essentially want to create the equilibrium in that closed system, measure it before any of this recirculation happens. That makes equilibrium never occur, essentially.
How did you say that it's artificially increased? I just missed that part.
It's artificially increased because as you trap CO2 in the lung bag system, the tissues continue to make CO2. And so that will always contribute to the lung bag system, which increases CO2 on the arterial side, which magnifies CO2 on the venous side, which prevents us from ever actually reaching equilibrium. It keeps creeping up and up and up and up and up.
Because there's CO2 in the bag that is being recirculated? Or?
It is because the bag system is closed. We don't allow that CO2 to escape, and we're always putting new CO2 in. So the tissues are always adding CO2. It's closed, nothing can escape, and there's a constant input of CO2. But if we could ever measure the equilibrium before that extra input, then we can approximate venous CO2 under normal circumstances. We want to be able to measure this, essentially, right? The 45 millimeters of mercury immediately incoming. So we want to measure the point of equilibrium, but we can't measure that because we never achieve it. So to get around that, we measure the rate of the increase of CO2. How quickly are you approaching equilibrium? And what we're looking at on this trace is something that you would get from lab. You have the average data for steady state that you use for tidal volume and VCO2 and percent CO2 at a given exercise intensity. And then you have the raw data, a breath-by-breath trace. There's a point at 3 seconds, and then at 7 seconds, and then 9 seconds. And each one of those data points, or each one of those rows, represents a breath. And so here we're looking at breath-by-breath continuous data for PCO2 if we could measure it constantly with the metabolic cart. And so normally you breathe out and we register some CO2. That's the gas exchange with the environment. And then as you breathe back in, it goes back down. You breathe out, register CO2, breathe in, little CO2. And that undulation is normal with tidal breathing. As soon as you clamp the system and prevent the escape of CO2, we start to see an accumulation. And so as I'm talking about reaching equilibrium, the overall trace here is reaching equilibrium. This would eventually, theoretically, reach a point where it would level off. That's what we want, that level off way over here on the right side of the classroom. But we never get there. So as we continue to breathe and the system is closed, we have an exaggerated increase in CO2. And then as we breathe in, it never returns to normal. And this accumulation continues until your subject can't contain their breathing. They can't stand staying on this closed system, or they're in danger of passing out, or we see recirculation and it's taken too long. But with all of these breaths, you're going to have data that looks more like these points along the graph. So this is continuous measurement. And we don't care so much about the valleys. We just care about the accumulation of CO2 at the end of each tidal breath. And so the points, P1, P2, P3 through P6, are points along that curve that describe how quickly you're getting to equilibrium. So what you're doing as you take this data is making this curve. And I just want, before we get into the mechanics of it, just appreciate from a normal end tidal breath, as soon as you close the system, there's a big jump in CO2. There's a large gradient. As you accumulate CO2, the next jump is smaller. The gradient becomes smaller as you approach equilibrium. The difference between the second and third is smaller than that, and so on and so forth. The difference, the steps between each point, gradually become smaller as you approach that equilibrium. And it's that characteristic that we're leveraging in our projection or in our estimate of equilibrium. The fact that the steps between points get smaller. And that's a natural characteristic of this equilibrium trace. So when you make this trace with your data, you have individual CO2% numbers for every breath. So you're plotting 1 point at this peak, 1 point at that peak. You've got 1 point as you close the valve. You've got a second point here, third, fourth, fifth. Those don't match P1 through P6. You you select points at equal time points, equidistant points. And the reason for that is not every breath is of the same duration. Some breaths are 2 seconds, some breaths are 4 seconds. And the accumulation is continuing between breaths. If you don't take equidistant points, the increase in CO2 is a factor of accumulation and a factor of time. If you have a 4-second breath, there's more time for CO2 to accumulate than if you take a 2-second breath. You don't want time to influence this equilibrium. You want the increase in CO2 to be due to the rate of accumulation only. And so if I have 1 second, 5 seconds, 8 seconds, 11 seconds that separate each of my measurements, I'm going to go back once I've made this trace, and here, this example is taking points that are exactly 2 seconds apart. It could be 3 seconds apart, it could be 4 seconds apart, but I'm removing time as a factor by setting the space between these points at 2 seconds. So I have P1 here at 9 seconds, I have P2 2 seconds later, P3 2 seconds after that, and so on. Equidistant values so that we can compare the increase in CO2 between points. It's important to get these points on the front half or early on in the rebreathe procedure, because if you wait too long and then some of that CO2 circulates back around, the curve never levels off. And so what I'm showing you up here is if recirculation were to occur, you'd never actually reach equilibrium. You'd have this gradual tangential increase in CO2 that persisted. You'd never actually reach a leveling off point. The rise would never slow. That's part of why it's really important to make this measurement early, collect all the data early, and then have these points fall on the early portion of the curve. You don't want them up here. So as we approach equilibrium, the amount of CO2 that we add to the system has less of an effect, has less of a stimulus in increasing CO2. The gradient becomes smaller. The step becomes smaller. we want to know, essentially, when is there no step? Right? There's a difference between the CO2 contents at P1 and CO2 content at P2. That difference is larger than the CO2 in P2 and P3. And it's larger than every subsequent step. There's going to be a point, theoretically, somewhere down the line over here, where P21 and P22 are the same. We want the point where there is no increase in CO2. That's the definition of equilibrium. And so one somewhat intelligent way to approximate that point is not to plot CO2 over time as it increases and then try to find the horizontal asymptote. It's to plot the difference between points. So on this plot, I'm showing you the CO2 of one breath, or the CO2 of one point on the x-axis, and the CO2 of the next point on the y-axis. And in the very first example, P1, P2, x and y coordinates, I have CO2 in the first point and CO2 at the second point. And I'm just plotting one breath or one point versus the next one. And all this is showing us is what we've already acknowledged. The difference between points becomes smaller over time. Here there's a large difference between points. CO2 is low in the first breath and it's higher in the second breath. That difference becomes smaller until there's some theoretical point way off on the right-hand side of the screen where P21 and P22 are the same. And if they're the same, they're going to fall on this magical line called the line of identity. And the line of identity has this characteristic where the x-coordinate equals the y-coordinate. 1 on the x-axis reflected in the line of identity gives 1 on the y-axis. 10 on the x-axis gives 10 on the y-axis. 100 on the x-axis gives 100 on the y-axis. That's a special line, the line of identity, where the x and y coordinates are the same. So if a point falls above this line of identity, the x-axis, or the x value, is smaller than the y value. The preceding point is lower than the proceeding point. If this line crosses the line of identity, wherever it crosses must be the point of equilibrium. Must be the point of equilibrium. We're never actually able to measure or observe this because of recirculation. If I overlay the recirculation curve here, you'll never actually get a crossing of this trace with the line of identity. But we can project the rate in the increase of CO2 as if it were not subject to recirculation. So I have an initial large difference, and that difference gets smaller and smaller and smaller until at some point the x and y coordinates would be the same. And that's the point where equilibrium would occur if we could observe it. We can't ever observe it. And so by putting these points on the graph and then extending, we're estimating where equilibrium would occur. And so now, if we have this trace with these data points, we can say the point of intersection is where CO2 in the lung bag system matches venous CO2. That's the point where equilibrium has been achieved. And that point of intersection, in this case, corresponds to 10%, 10.08%. And that's a random arbitrary number. It's going to be different depending on your exercise intensity or depending on your person. But for the example, they cross at 10%. They might cross at 8%. They might cross at 11%. You're never going to observe the cross. We are extending it from the data points that we do have.
Sorry, could you say that again? I just missed the wording. So the intersect between the line of identity and the other lines, I forgot the name. What does it represent again?
The intersection point between the line of identity, which is here,
Yeah.
and then the trace that we've generated, the difference between CO2 in two subsequent points, where they cross is equilibrium. That is, two subsequent points have the same concentration, or are at the same percent CO2. So 10.08% on the x-axis is 10.08% on the y-axis. P21 and P22 have the same percent CO2 when they cross the line of identity, by definition.
Like between 2 points, there's no, they have the same value of CO2.
Between two subsequent points, there is no difference in CO2, which is the definition of reaching equilibrium. Yeah.
The equilibrium is between venous CO2 and what was the other value?
The equilibrium is between venous CO2 and then CO2 in the lungs.
Okay.
So alveolar CO2, end-tidal CO2. CO2 in the air in the lungs. It would be in equilibrium with venous CO2 at the point where these two lines cross.
And it's like a theoretical point because of recirculation.
It is a theoretical point because we'll never actually measure the horizontal equilibrium. We'll never measure 2 points that have the same CO2. 2 points will never have the same CO2 in practice because this collection takes too long, and the venous blood recirculating to the heart and the lungs will add CO2 to the system, and it will always creep up. We'll never actually see the equilibrium, but we can estimate it from the points on the onset of this curve. Early on in this curve, no extra CO2 has been added to the system. We're still waiting for the 40, 41, 42, 43 to come around the arterial side and return back to the lungs. That's why it's important to make this measurement within at least 20 or 30 seconds tops.
So then why do we do rebreathe for 30 seconds? Just because we like to watch people squirm, or?
The rebreathe for 30 seconds probably is to make sure that you have all of the data and you're never missing out on any data. The rebreathe for 30 seconds is it's a way to set the high water mark. If you can get that far, great. You're not going to use data from 25 to 30 seconds, but you're not going to be at risk of missing any of the data either. If your subject also can't stand it, they can kick the mouthpiece out 20 seconds in, but it's a general number to set your expectations for the maneuver. Yeah. And those of you that did it in lab last week during exercise might have only lasted 12 seconds or 15 seconds. What's that?
Peter did great.
Yeah?
He hit 30 for everyone except the last.
How'd it feel?
Awful.
It's really odd, isn't it?
Yeah, it feels like you're not breathing.
Feels like you're not breathing. Yeah, that's exactly right. Because it's warm and it's humidified air, which isn't normal. Yeah. You taste that tinny feeling too? It's like metallic. Yeah. For those of you doing the maneuver this week, or anyone next week or the week after, because there's 4 weeks of rebreathes, If you can't make it 30 seconds, don't force yourself, okay? 30 seconds is a general direction. If you can't make it that far, don't force yourself, especially at the intense exercise. So all we want is the point where these lines cross. The point where two subsequent p-values have the same percent CO2. That means the curve would have leveled off and there's no increase in CO2. They're at equilibrium. That point by this graph is 10.08%, and now I can take that and transform it just like I did for the arterial values. 10.08% is not concentration. It's not even partial pressure. And so I need to figure out the partial pressure represented by that number before I can figure out contents. Partial pressure, very easy. 10% of the pressure in that system is due to CO2. So 10% of atmospheric pressure is due to CO2. I can plug the numbers in directly. 10.08 over 100 of the atmospheric pressure when we correct for water vapor means 71.87 millimeters of mercury is our partial pressure of CO2. This is the partial pressure of equilibrium between the venous and the end tidal CO2s. This is where equilibrium would occur if we could ever observe it. But we need this to not be partial pressure, we need it to be contents. So we take this number, and much like we did at the start of class for the arterial side, we transform this to contents. And this is an example. I mentioned to you that I'm going to change this in the coming notes. This is an example of how that would change so you don't have to do the correction for units right at the end. The equation now is slightly different. It still allows me to input the partial pressure of CO2 directly and then resolve the equation directly. But when I resolve it, I end up with mils of CO2 per liter of blood. This is the equation that describes contents in mils of CO2 per liter versus partial pressure. Notice between points A and B, it's pretty direct. There's no circumventing the contents calculation. We had to stop off and account for the dilution of air on the arterial side, because as we measure it at the mouth, it had mixed with environmental air as it left the lungs, and CO2% or CO2 contents decreased. Here we don't have to do that. And we don't have to do that because there's no dilution, or at least we are removing the dilution from the lungs. As we approach equilibrium, as CO2 accumulates in that system, we are removing the dilution effect of environmental air. There is no more air to dilute CO2. You're forcing equilibrium. You're accumulating CO2 in that closed system. There's no environmental air to obscure the value. There's no contamination. Yeah.
Is the 0.014, is that a constant?
It is a constant.
Yeah.
And I will briefly put this slide back up, which we looked at on Thursday, which is just the characteristic of oxygen and CO2 to dissolve in blood. If there is a pressure, shown here on the x-axis, that relates to a contents on the y-axis. And because this is in mils per 100 mils of blood, the original equation, which I've actually changed, was 11.002. But what I'm doing is expanding this so that instead of showing mils per 100 mils of blood, I'm going to expand it to mils per liter of blood to circumvent the fact that we have to correct for units and then give this equation directly. So this is describing this line. That is a constant equation. Different for O2, but both specific to blood. So it's just describing if there's a partial pressure, this is how much of that gas is in blood. So we are forcing equilibrium, and you're removing any effect of the environmental air. There is no need to correct, because throughout the lung bag system, gas concentration is the same. In the alveoli, in the bronchioles, in the trachea, in the bag, gas concentrations are the same. Nothing obscures that number. So now, all of the animations have disappeared. So let me just quickly set those back up, because I don't want to overwhelm you with animations or with numbers and fractions and all that stuff at first. Okay, and then I want these to move down. Okay, trust me, it's for the best. So we have contents values for the venous CO2 and arterial CO2. We have VCO2, which is the rate of CO2 production. Now we can put all those values in to calculate cardiac output. Numbers shown here are what we have devised in our examples. VCO2 we calculated on Thursday as 440 mils of CO2 per minute, or you've taken it from the metabolic cart trace at steady state for a given intensity or rest, 440 mils of CO2 per minute. And then the venous and arterial CO2 contents are simply listed here. So the venous that we just calculated is 611.91 mils of CO2 per liter. And then we finished calculating this at the start of class, 490.57 mils of CO2 per liter. If I just resolve what's in the brackets first, it's a direct subtraction. 121.34 is the difference in venous and arterial CO2. So that is the difference in venous and arterial CO2. Now I want to isolate Q. And so to isolate, I can simply divide both sides of the equation by the term in brackets, 121.34 mils of CO2 per liter. If I do that on this side, I'm left only with Q. If I do it on the left-hand side, and I've swapped the equation just for ease of representation, 440 divided by 121.34, I've got mils of CO2 per minute left over here on the left-hand side of the equation. And I want to divide by mils of CO2 per liter of blood. If you divide by a fraction, if you think back to grade 9 algebra, you multiply by its inverse. So dividing by mils of CO2 per liter is the same as multiplying by its inverse, liters of blood per mil of CO2. Luckily, you also remember from grade 9 algebra, if there's the same term on the top and bottom, those can be removed. And now all I have to do is divide 121.34 into 440, and I'm left with liters of blood per minute. Liters of blood per minute. This is the reason why I didn't want to worry about 100 mils of blood and did the correction before inserting the numbers here. Liters of blood per minute. 3.6 is the cardiac output in this example. A typical resting cardiac output. It will be much higher with exercise. It can border on 20 liters per minute in some cases. I think the highest ever has been in the 40 range for a very cardiovascularly fit individual or highly trained elite individual, but certainly no more than that. And it shouldn't be any less than this either. This is about as low as you would expect to observe in lab at rest. So as CO2 accumulates in that system, it will reach a point where it matches venous blood. We never observe it, but we can project and estimate where that equilibrium will be by looking at how how subsequent points change. And where there is no difference between 2 points gives us the venous CO2. In combination with the arterial CO2 and VCO2, we can then calculate cardiac output. Which allows us now, if we have heart rate, to calculate stroke volume. If we take blood pressure, we can calculate total peripheral resistance. Now that we have this number, those main physiological equations are opened up for us. So, I know that's a confusing idea. Does it at least make the majority of sense? There's going to be some things you have to review, but does the concept hold up? Pretty good? Okay. So I want to add some clinical spin to this. In calculating in calculating cardiac output, what are the situations where cardiac output is ever compromised? And so I think that is best typified by a discussion of congestive heart failure, which largely results from hypertension. So we've talked about some cardiovascular issues in the ECG section. We've talked about hypertension as well. And so I'm going to bring them together in how they culminate to compromise cardiac output and lead to congestive heart failure. This will be the last major section in this series of slides. I have some at the end that deal with how dehydration mimics this phenomenon, which leads into labs next week. But we're going to first talk about what kinds of heart failure there are. There are systolic and diastolic. Also left and right-sided heart failure, which are technically different. And while they're also separate, left-sided tends to lead to right-sided heart failure. And in leading to right-sided heart failure can exacerbate conditions like COPD. So we'll talk about those briefly. And I think that it's really important to review the elements of blood pressure control which underpin the flow volume loops of the heart. So preload, afterload, contractility, understanding these in a bubble, and then trying to figure out how they're altered in a situation of congestive heart failure and how multiple factors can be altered at once can lead us to understand how cardiac output is compromised. And then understanding that Q or flow is insufficient, what is the chronic downstream long-term effect of that? Measuring cardiac output on a minute-by-minute basis or at different exercise intensities is one thing, but if there's a persistent undersupply of blood to the tissues of the body, what does that mean? And this is another spectrum type disease. It's a gradual progressive disease that leads to a systemic attempt to correct the lack of flow. The lung is at risk, the kidneys are at risk, the heart tries to compensate, but overall, flow remains inadequate. So why is it inadequate? What compensations are attempted? And then why don't they work is really the focus of the second half, which will be Thursday. So let's talk about heart failure. In simplest terms, systolic heart failure is the inability of the heart to pump blood to the systemic circulation. The inability of the heart to pump blood to the systemic circulation. In this case, flow is compromised. The output of the heart in liters of blood per minute is lower than it should be, both at rest and during exercise, continually lower than it should be. This is specifically an inability of the heart to pump the blood that it has available. And this differs from diastolic heart failure, which is an inability of the heart to load enough blood to pump. In both cases, cardiac output is compromised. But the reason for that compromise is different. So in systolic heart failure, there's some obstruction. There's some deficiency of normal function of the heart that it can't supply blood to the periphery. In diastolic, there's some deficiency upstream of the heart in loading or supplying the heart with blood to be ejected. These don't necessarily overlap, but they do often occur in tandem because systolic heart failure, being the most common, often leads to diastolic heart failure. And it leads to diastolic heart failure through an inability to pump to the systemic circulation, which, if you follow the loop in its entirety, means inability to pump to the systemic circulation also includes the heart, meaning an inability to return enough blood back to the heart on its way through the systemic circulation. So they are technically separate ideas, but they often do occur together. And if they don't occur together, systolic heart failure is often more common and can be a prerequisite for diastolic heart failure. So systolic heart failure, being our most common, is largely modified by pressure sensed in the periphery. Right? Pressure is the controlled variable. Pressure is the variable that dictates cardiac output. Pressure in the systemic circulation is what modifies cardiac output. And so returning to our understanding of blood pressure control, we know there are sensors that will monitor pressure in the periphery, baroreceptors in the aortic arch and the carotid sinus, that take some input or some tonic signal and compare it to a normal value in the blood pressure control center, here specifically in the medulla of the brain. And then if the comparators are off, if there's a discrepancy, the brain controls some output mechanisms. If blood pressure is too low, we activate these mechanisms to increase pressure. If pressure is too high, we deactivate these mechanisms to reduce pressure. Overall, the effect is to restore whatever is being sensed to a normal value. And this should not be a surprise or any new information. But what we're going to look at are the ingredients of this response. So we have the SA node and the AV node that can be stimulated, the arterials and the venules that can be stimulated, all to affect individual items in this equation. Now I've taken and unpacked the equation that I introduced in the previous section a little bit. Mean arterial pressure, or blood pressure, is flow times total peripheral resistance. And here I'm simply unpacking flow to be the combination of heart rate and stroke volume. We know that to be true. Liters per minute is a function of per minute and the liters per beat. So we want to look at how these individual values are changed. We know the framework that controls them, and now we're going to look at how we modify each of these factors. So from the aortic arch and the carotid sinus, this is a depiction of the relay anatomically. We have the sensors shown here that relay information to the medulla and also the cortex in this case. Some reflex that sends effector signals down the spinal column to the to the AV node and the SA node, to arterioles and veins that are not shown on this figure. Overall, if we have a drop in blood pressure, we act to activate all of these effectors. So if we were to activate arterioles and venules, not shown here, we have this stimulation and this positive effect of vasoconstriction, increasing pressure and increasing venous return. On the heart side, we have three different possibilities. We can activate the heart muscle or the heart as an organ in three different ways. So increasing the rate of contractility, the rate of firing, is what we call a positive chronotropic effect. Increasing the firing rate of the SA node to increase heart rate is a positive chronotropic effect. Often overlooked, but in line with this chronotropic effect, the firing rate, is facilitating the speed of signal conduction. That is a positive dromotropic effect. We can increase the speed that action potentials are sent through the conducting pathways of the heart. And it's often overlooked because that must happen in order for heart rate to increase. Technically, technically the chronotropic effect is signal arriving at the SA node, and then heart rate increasing would be an effect of the positive dromotropic effect, the signal being transmitted faster through the conduction pathways. Yeah, your question?
Yeah. Are these necessarily in a chronological order?
No, they are just describing the types of responses. It's not what happens first, second, or third. These are all of the stimulatory responses listed on the slide. So increasing the frequency that the heart sees the action potential, increasing the speed of the action potential, and then the inotropic effect is the increased contractility of the heart, the force of contraction. All of these combined features would react to a decreased cardiac output or a decreased blood pressure. And the opposite would occur if we observed hypertension, a high blood pressure, to relax the arteries, to relax the heart, and bring pressure down to normal.
What did you say the inotropic was? Sorry.
Inotropic, the positive inotropic effect is an increase in contractility or the force of contraction. So the outputs to the heart, which would act to increase cardiac output in a situation where it's deficient, would try to make the heart beat faster, send the signals through the heart more quickly, and then forcefully contract the heart, increase the force of contraction to expel more blood. So we're just putting names to the phenomena that I think you already have a handle on, that you already know. Yeah.
Could you go over the chrono and the dromo one more time?
Sure.
I'm just struggling to understand the difference.
So the positive chronotropic effect is increasing heart rate. So it's the signals being sent to the SA node to depolarize the SA node to initiate a cardiac cycle or
So there's more
contraction.
signals being sent.
more signals being sent.
And then the dromo is the signals are being sent faster.
And the dromotropic effect is the speed of the signal being sent through the heart. So it goes through the heart to disperse through the heart and initiate contraction faster.
Okay.
The dromotropic effect is the speed of action potential.
So chrono is like to the SA node,
velocity.
and then dromo is SA to the rest of the heart.
Yeah.
Okay.
Yeah. So, if congestive heart failure is an issue, and we'll see why it's an issue, these are the typical responses acutely to restore insufficient cardiac output. This is what would try to correct congestive heart failure from the point of view of blood pressure regulation in an acute manner. Now, I find it's helpful to consider not only heart rate and stroke volume in trying to interpret the functioning of the heart, but to consider the pressure volume cycle of the heart, a lot like we did the flow volume loop during the forced vital capacity test. Proper function of the heart is not only how quickly it's beating, or what stroke volume is, or is cardiac output sufficient. And it's the combination of many variations of the pressure volume cycle that determine if, essentially, cardiac output is sufficient. So one pressure volume loop is what I'm going to lead you through here, just to show you the elements of the pressure volume cycle. We first have the mitral valve opening, and I'm picking this as my arbitrary start of the cardiac cycle. The mitral valve opens, which indicates the left ventricle is filling. Mitral valve opens, which indicates that the left ventricle is opening, and this is in the hopes that we're going to pump blood to the systemic circulation. What happens in this pressure volume cycle to allow that? So mitral valve opens, and we have filling of the left ventricle. There's some initial volume. It's never completely empty, and here I'm showing it starting at 60 milliliters. There's some blood in the ventricle. And then as it fills during diastole, we've doubled the volume. We're at 120 mils. Pressure is increased somewhat, just because the walls of the ventricles are expanding as blood fills the ventricle, until we reach the point of end diastolic volume. The heart is, or the ventricle is, as full as it's going to be for contraction to occur. At this point, when we've reached end diastolic volume, the atria have done their bit to pump and fill the ventricles somewhat, or as full as they're going to be. This is part of why pressure's increased. And the ventricles start to contract. Because the pressure starts so low, nothing happens at first. The ventricles contract, they generate pressure, cardiac muscle shortens, force increases, but volume doesn't change. So as the ventricles start to contract, what's not written here that should be fairly obvious is the mitral valve closes. There's no escape for the blood in the ventricle. As contraction proceeds and pressure builds, we're in a phase called isovolumetric contraction. So volume stays the same while contraction proceeds. Pressure in the ventricle increases to a point where it supersedes the pressure in the aorta. At that point, simply by the difference in pressure, or the gradient that we're establishing, the aortic valve opens, And as soon as that occurs, blood starts to pour out. So the volume starts to decrease. As soon as the aortic valve opens, volume starts to decrease. Pressure doesn't stop being generated. The ventricle is still contracting even though the aortic valve is open, and we can see that because pressure continues to rise. The only reason pressure rises is because the heart is contracting. Pressure in the ventricle will eventually peak. It will eventually peak at systolic pressure. And then as it approaches the length of, or the terminal length of contraction, it generates less and less pressure near the end, and pressure starts to drop. Eventually, end systolic volume is complete contraction of the ventricles. All the blood has been emptied out that will be emptied out, and the ventricles relax. At the end of systole, relaxation occurs. Pressure in the ventricle is now less than in the aorta, and so the aortic valve closes. There's no change in flow or volume. The muscle is simply relaxing, tension is dissipating, pressure is falling. And pressure falls until it reaches a point where it establishes a new gradient. If pressure falls to a point lower than the pressure in the atria, the mitral valve opens, blood flow occurs, and the entire cycle continues again. So this typifies one cardiac cycle from the point of view of the left ventricle. And there's no information on heart rate from this loop alone. If you counted the number of loops in a certain period of time, you could figure out heart rate. But we do get some nice information about stroke volume. The difference between end diastolic volume and end systolic volume along the x-axis will be stroke volume. And we also have an idea of the pressure generated in order to allow the heart to pump blood. This is a normal, healthy individual. What's diastolic pressure?
Just asking in this case or in general?
In this case, what is diastolic pressure? Around 80. Why do you say that?
Well, it's the final pressure before the aortic valve opens.
Right. Exactly.
Would be when you start hearing noises.
Yeah. So diastolic pressure is the resting tension in the arteries, in the systemic circulation. As soon as the heart crests or rises above resting tension, resting pressure, the aortic valve opens, and the point where it opens is at 80 millimeters of mercury. Absolutely. This is the point of diastolic blood pressure. And similarly, the peak pressure we observe during contraction, the highest point on this graph, is systolic blood pressure. I find it really interesting to think about why does the aortic valve close at a higher pressure than it opens? If resting systemic pressure is 80, and that's the point where the aortic valve opens and blood starts to be ejected, why doesn't it close at 80 as well? Yeah.
Is it because of the rebound in the arteries?
Okay, because of the rebound. What do you mean by rebound? I think you're right, but what do you mean?
So because when you push something through an elastic artery, like the
Okay.
aorta, that when it rebounds, it's pushing through with greater pressure than what the heart actually exhibited initially. So they're pushing through the rest of the system.
Okay. So what you're describing is a cascade of pressures almost. The heart generates some pressure, and then pressure is in the aorta, and that forces the walls apart, and the elastic recoil creates a pressure, and then that echoes through the systemic circulation and allows the flow of blood? Yes, I think so. I think of it as the heart pressurizes the blood. And this is a very segmented, literal approach. But if the heart pressurizes the blood, and then the blood is in the aorta and it's pressurized, and it's the pressure that allows that flow to occur, the echo that Dylan described, pressure doesn't only flow in one direction, it also flows back. So the pressure in the aorta is higher than resting during systole, right? It's on its way back down to resting, but it's higher than resting. And so it doesn't have to close at resting pressure, it just has to close at the point where pressure in the arteries is higher than pressure in the ventricles. It's just interesting to think of, why is this point so much higher? And that might not be the right reason, but it just closes at the point where pressure in the arteries is higher than pressure in the ventricles. So I'm going to use this as the framework to describe the factors on, or most of the factors on the last page. When we try to recover an insufficient cardiac output, when we try to restore normal function, what does it look like in terms of the pressure-volume cycle? So the easiest, I think, to describe is that of preload. Adequate venous return. Preload, afterload contractility. It's not an immediate one-to-one parallel of the factors on that last slide, but preload is one of the factors that allows us to modify cardiac output. It's also one of the factors that might account for a deficiency in cardiac output with congestive heart failure. But the Frank-Starling law of the heart describes preload. It says essentially, if you have more blood available, more blood will be pumped. That is the Frank-Starling law of the heart. If more blood is available, it will be pumped. And so using the normal scenario shown here, when preload was increased, how might that look? Will you see it? Okay, I'll show you. If preload is increased, that means that there is more blood available at the onset of systole. There's more blood available at the end of diastole. So where we would normally observe end diastolic volume here, if we increase preload, we shift that point to the right. Notice, if we increase volume, we also increase pressure. We're following the length tension curve of the muscles in the heart. The more we increase volume, the more that muscle is stretched, the more pressure there is within the ventricle. If you kept loading and loading and loading, you'd reach a point, well, you would also continue to increase pressure as well. So if we increase end diastolic volume, pressure is somewhat higher. During systole, the heart still contracts. Volume doesn't change initially. Ejection still occurs when we reach the resting systemic pressure, 80 millimeters of mercury in this case. And the heart continues to function normally, ejecting to that same end point, and the systolic volume is the same. The only difference is we've ejected more blood. From a higher end diastolic volume to the same end systolic volume, preload increases stroke volume. If you load the heart with more blood will be pumped. The counterpart idea to this, I would consider as contractility, the forcefulness of ejection. If you contract more forcefully, more blood will be ejected. In this example, end diastolic volume is the same. We follow the same pressure curve and eject blood along the same trajectory. But if the heart muscle is contracting more forcefully, generating more force and generating more pressure, one, we observe a higher systolic pressure, and we squeeze the ventricles more. More blood is ejected. Lower end systolic volume, but the same end diastolic volume, again, means more stroke volume has occurred, more blood has been ejected. You can start to imagine, what if contractility and preload were both increased? You'd have an additive effect. Now, the mechanisms I described on the last slide do help the heart to increase output. They also work against the heart by increasing the opposition to flow. So, universally, the response to a decrease in flow is a sympathetic response. Activate the heart, speed it up, contract forcefully, vasoconstrict, to bring pressure back to where it should be. And in terms of cardiac output, so far, the elements we've discussed are beneficial. We can increase preload to eject more blood. We can contract more forcefully to eject more blood. Vasoconstriction works against us. And vasoconstriction of the venules and the arteries is what we describe as afterload, or the pressure against which the heart must pump. An increase in afterload is an increase in the resting systemic pressure of the arteries. In a situation where afterload is increased, the heart fills just fine. End diastolic volume is the same. But because the resting systemic pressure is higher, the period of isovolumetric contraction is longer. We need to reach a higher pressure in the ventricle before the aortic valve opens. Here, that pressure looks to be around 100 millimeters of mercury. So afterload is diastolic blood pressure, essentially, the resting systemic pressure in the arteries. So the heart continues to contract, reaches that point, trying to think of a way to describe this in a way that doesn't complicate or confuse matters. The entire span of this contraction, as we contract, generate pressure, eject blood, happens along the length tension curve of the cardiac muscles. So there's some overlapping fibers, and they shorten and contract, and you know that there is an optimal length to give maximum tension, right? Just because we're generating more pressure doesn't mean that we have more shortening ability. A greater pressure to overcome essentially means that we're generating more pressure and we've shortened those muscles more to achieve that pressure. And therefore they are further along in the contraction cycle. They can't eject as much blood, they can't shorten as much as they would in a normal situation. So because there is a higher afterload, the pressure at which we start to eject blood is further into the contraction of the cardiac muscles. That leaves less ability for those muscles to shorten and eject blood during systole. The result of that is end systolic volume is higher. we're left with more blood in the ventricles. The result, then, is that stroke volume is decreased. So stroke volume is decreased, yet this is part of the response to restore pressure to normal. Is this a major factor? It's kind of a loaded question. What if I say it's not a major factor? It's not a major factor. Why would I say that?
Because your heart rate compensate in different ways to make up for the decreased stroke volume. Like increasing heart rate.
Okay. Yes. Your heart does compensate in other ways to make up for the decrease in stroke volume. Increasing heart rate is one of them. Increasing preload is another. Increasing contractility is a third. The elements that we listed on the effector slide outweigh the negative influence of this increase in afterload. What I like to think about is exercise. Move to exercise, massive sympathetic outflow. Pressure increases, heart rate increases, stroke volume increases. This should happen during exercise. We have a higher mean arterial pressure. Afterload is higher. Yet, we observe an increase in cardiac output. We observe and can calculate an increase in stroke volume. We can observe those at the whole body level. You will do that in lab. You've seen stroke volume go up. This happens behind the scenes, but it's overridden. It is overridden. It must not be a major factor. Pressure in the systemic arteries does go up. It works to decrease stroke volume, but you watch stroke volume go up. You can see it go up in practice. This must be overridden. Okay, I'm going to leave it there. With this understanding, we're going to look at congestive heart failure on Tuesday. How this goes wrong, what about the pressure volume cycle is compromised, and how that leads to COPD and other nasty side effects. A lot to cover in one day, but good on you for staying with me.